Good morning, everybody. How's everybody doing? Just say hi to me in the chat if you're there, so I can know who all's here today. If you haven't checked already, I did grade your tests from last time, and so your grades are all up for your tests. So good job with that. Most of you guys doing fine on your tests. Let's see. So today we're going to be looking at sound. I'm sorry I put it up a little bit late yesterday. Well, late as in like late morning, 9-ish or so. I put up a whole bunch of links to different videos that I wanted you guys to watch. Did you guys end up actually watching those? They weren't too long. I think one of them might have been a little bit longer, but they weren't too long. Altogether, it should have been less time than class time. So hopefully you guys were able to watch those. Some of them were pretty interesting. You could actually get to see the sonic boom on some of those airplanes, and there was a rocket ship that you could see the waves on. So those were pretty cool videos, I thought. And that one that actually was producing the sound was pretty cool to give you guys a visual look at what this whole idea of the Doppler effect really is, and also a look at how it can be used for radar and all that kind of stuff. So hopefully you guys saw those videos. And if you didn't, make sure you go to Google Classroom and click on each of those videos. They're not too long, and you just watch them and learn a little bit about the Doppler effect and all that kind of stuff. Where the links in Facts, Google Classroom, not in Facts. So sorry, I did not post them to Facts. I just put them all in Google Classroom. And I think it was a little late yesterday. I had them all posted by like 9 o'clock, 8:30 or 9. So I know it was after class. So sorry about that. You could just go back and watch them anytime. It doesn't take that long to watch them all. Okay. Let's see. So today we're going to go ahead and get started talking about that. Hopefully you guys did your assignment. I don't know, did you guys do your formative assessment assignment that was due today? If not, let me see. If not, we can just skip this, and then I can just talk about it later. So formative assessment. I know we just had a test, so you guys are probably not thinking about that. But were you guys able to do that formative assessment? This one right here. Let's see. Yes. Okay. So we're going to go ahead and go over the formative assessment, which is good that you guys did that. And it shouldn't take too long, actually, because some of these answers, and I don't even know why I skipped number 2 or 6. So we could literally go through all of them. I should have just assigned the whole thing to you, because it's actually not that much work. So let's go through the formative assessment. Then we're going to talk about sound intensity and do the sample problem A in your book. All right. So formative assessment, what's the relationship between frequency and pitch? And so frequency and pitch are, they are directly proportional. So as the frequency goes up, the pitch goes up. And pitch is specific to sound. It's just a quality of sound, of how we perceive sound. And frequency is just a concept for any kind of wave. But frequency and pitch, they go together. As one goes up, the other one goes up. They are directly proportional. Number 2. Now, I don't think I even assigned number 2, but I think as I was looking at it this morning, I thought it looked like a pretty cool question. So this dolphin echolocation, and that's basically dolphin sonar, right? And so essentially the dolphin sends out like sound waves, and they come back and they hit the dolphin, and the dolphin's able to determine where different objects are. So the question, so it's kind of a long question, but the real question part of the question is right down here. But only those at the upper end of this spectrum are used in echolocation. Okay? Explain why high frequency waves work better than low frequency waves. So I didn't actually ask you guys this, but does anybody have an idea why that might be? What do you guys think? Why are the high frequency waves used but not the low ones. I'm going to actually come back to that, so you guys can think about that. Let's go ahead and answer the ones that I actually did assign for you guys, 3, 4, and 5. All right. So sound pulses emitted by a dolphin travel at 20 degrees ocean at this incredibly fast speed, right? 1,450 meters per second. However, in air, they travel at only 342.9 meters per second, of course, depending on the temperature there. How can you account for this difference? The difference in speed is essentially accounted for because the air and water have different densities. And so sound is a wave that travels through particles bumping into each other. Right? Sound waves require particles, whether it's air particles, solid particles, liquid particles, whatever, they have to bump into each other. And so it's a vibration wave, right? And as these things vibrate, it's able to propagate the sound through whatever medium it's in. In air, the air particles, the gas particles are further away from each other, so it's going to be more difficult, and it's going to take them longer to bump into each other. And so in water or in a solid, the particles are closer together, so we would expect that the sound travels faster, which it does. So it's differences in densities or differences in how far away the particles are from each other. Okay? Number 4, could a portion of the innermost wavefront shown in this figure be approximated by a plane wave? And the answer is no. The reason is, in the innermost part, it's very, very curvy, okay? And so the closer you are to the source, the less like a plane wave it is. As it gets further and further and further out, the more like a plane wave it is, and that's just simply because the bigger the circle, the less curvy in terms of an absolute amount of curviness, okay? And so we can realize that by looking even at the world, right? So as the Earth, we stand on the Earth, the Earth looks like it's flat as we look around us, but that's just because the Earth's really, really big. So the bigger the wave, the further away you are from the source, the more it can be approximated by a plane wave. And we can see that out here, it's the surface of this wave here is flatter than close into the source. It's more curvy close to the source. So that's why you would say no for number 4. All right. And I get an answer for number 2. They are farther reaching. No, that's not what is really going on for that. All right, we'll get back to that. We'll get back to number 2. It's not that they're far. Oh, another answer. It's because they're smaller or more compact. That's correct, but why would being more compact be better? So think about that. So they're more compact. Why would that be better? And we'll get to that. I'm going to answer 5 and 6, and you guys can still think about number 2 there. All right. So you have this tank here, and the Doppler effect. You guys should, if you watch the videos, you'll become an expert in the Doppler effect. Definitely recommend that you watch those videos. They're pretty cool. Okay. So this one, what's going on? Basically, this thing is emitting sound, and it must be moving, or the tank that it's in must be moving. But this one, number 5, it's moving within a ripple tank. And so what's going on? This thing must be moving to the right. Why? Because as it's emitting waves, this thing is getting, the waves are getting bunched up here and getting spread out here, which means this object must be moving to the right. Okay? Now, if this source was stationary, so number 6, if this source is stationary, it would mean that the tank is going to be moving to the left. And so that's kind of something that we've covered before in terms of relative motion. So the two are equal. Either this is moving to the right or the tank is moving to the left. We get a relative motion of this with respect to the tank going to the right. So that's it. Let's come back to number 2 and say, okay, why is that? At higher frequency, those waves are more compact or closer together, and that's going to enable the dolphin to get more detail in whatever it's looking at. So what do I mean by that? Okay, so if we have, some kind of, this is going to be a terrible drawing here, but if we have, some kind of fish over here, and this dolphin is sending out waves. If it was a low frequency, what's going to happen is low frequency means that the waves are further apart, and when they bounce back, they're still going to be further apart, and they're not going to be able to give a whole lot of detail. So that's a low frequency kind of situation. High frequency means that those waves are going to be closer together. Okay? And if those waves are closer together, the dolphin's going to be able to get more detail. Right? The closer those waves are together, the more detail it's able to pick up on. Okay? And that's really what's going on there for the echolocation of dolphins. And in essence, the higher the frequency, the closer the waves are together, and the more detail that you can get in that reflected wave. Okay? And this similar kind of situation, but not the same. Okay, so similar situation of these days when they're working on making smaller and smaller and better computer chips, they need to use, let's say, even the invention of the Blu-ray. What's the whole idea of the Blu-ray versus the regular DVD is that when you have higher frequency light waves, you can get to smaller features on the disc or on the chip or whatever else. So we use light to print things on computer chips. We use light for, DVDs and Blu-rays and all that kind of stuff. And when you have a higher frequency, smaller wavelength light, you are able to get more detail in the object. Okay? And so this is a phenomenon that's both for sound and light. All right. So that's it for the homework. Hopefully you guys got that. All 6 of you who are here online with me. All right. And we can go ahead and talk about the new stuff for today. All right. So new stuff for the day is going to be about sound intensity. Right. Sound intensity. Okay. And let me just give you a heads up about what we're going to be talking about in terms of sound. There are 3 main characteristics of sound that we're going to be looking at, and that's going to be the power of the sound or the power of the thing that produces it, the intensity of the sound, and we're also going to look at the decibels of the sound, which you've probably heard about. Now the decibels, this is a log scale, okay? And we're going to talk about that. The intensity is just an absolute, like an actual amount of sound intensity. I don't even know how best I could explain it. The absolute amount of sound intensity at a particular point. So wherever you are, there's at any one particular point you can talk about the intensity. The power is more to do with the amount of energy per time at the source. Okay, so the source is going to be emitting a certain amount of sound, right? And we can talk about how much sound it's emitting by the power of the sound. And power generally is going to be, power is energy, some kind of form of energy over time. Right? We've defined power before as work over time, but it can also be energy over time, any form of energy, whether that's a work, heat, or just a sound energy. So it's energy divided by time, so the amount of energy per time. Intensity is more looking at the observer. So the power has got to do with the source of sound. The intensity has got to do with the observer or where you're listening to the sound, as does the decibels. Okay? And so because sound waves, they propagate pretty much in all directions. So unless you have some device that limits the movement of the sound is going to be omnidirectional. That means it's going to be going in all directions. So let's suppose we have some sort of point source here, and that's generating sound, that sound is going to be moving in all directions away from it. All right, and as long as that point is not moving, the sound is going to be equal distances as it goes out. Okay, so given, like, let's say after, I don't know, a fraction of a second, the sound wave is right here. After another fraction of a second, it's here, and then here, and then here. And so you can see as the sound propagates, as time passes, those sound waves get further and further away from the source. But they do that in sort of in a sphere, okay? And so at time t, right, the sound is going to be in this one big wave, and it's equidistant from the source. As long as the source isn't moving at all, right, that sound wave is a distance r away from the source all around it in basically the shape of a sphere. Now, obviously, if you have objects around it somehow, they might absorb that sound or reflect that sound and make everything complicated. But we're just talking about some point source that's not being, the sound isn't being affected by anything else in the room, okay? And so because of that, you would expect what? You would expect that the further the sound gets away, the weaker the sound is, right? The further the sound gets away from the source, the weaker it is, because it's getting more and more spread out, right? So you start at some little point, and that wave propagates out and becomes, this big. If you wait even longer, it's going to be even further away from the source. And that coincides with our everyday experience, right? The further away you are from a sound source, the less loud it sounds. And that makes sense, right? And so we have a way to calculate this, right? The intensity looks at that sound, the amount of sound that any particular point in space is getting based on how far away it is. Now, in order to look at that sound intensity, we have to think about, well, what really matters here? The sound itself is going to be along this shell. You can think of this as a shell. So as the wave propagates out, it's no longer in here, but it's just along the surface. So we don't care so much about the volume of this cube, but we care about the surface area of the cube, because the wave front is only on the surface, kind of like a shell, all right? And so to remind ourselves a little bit of math geometry, the surface area of a sphere is what? It's given by 4 pi r squared, okay? So to calculate in a very simple way what the intensity of sound is given by the equation of the power divided by 4 pi r squared. Very simple equation, okay? So you have the power, which is the amount of sound being generated at the source, divided by the surface area of that sphere. So if you're whatever 1 meter away from that source, r is going to be 1, okay? And so this is our intensity equation, and we can rearrange it to solve for r or to solve for the power, but that's our equation that we're going to be using. So let's go ahead and open the books and look at the sample problem, and then we'll be done. So short class a day. So just a heads up, we are not going to have class tomorrow because tomorrow's a Thursday, and but we are going to have homework that's due tomorrow. So just for your reference, what I'll probably do is I'll just take a picture of the answers and send it to you guys after the homework is due, so you guys can check your answers. But we're not going to have class tomorrow to talk about the answers to the homework. So just keep that in mind. I will send those out to you guys on Google Classroom, or I may just send an email out. All right. So let's see. Where is sample problem A? Here we go. Sample problem A. What is the intensity of the sound? So we're solving for intensity. Waves produced by a trumpet at a distance of 3.2 meters when the power output of the trumpet is 0.2 watts. assume that the sound waves are spherical. No, this is not a homeschooling session. We are actually a school. All right, but whatever. We're talking about physics here, so we can answer your physics questions if we're talking about sound specifically. All right. So what we're doing here is we have a trumpet, and that trumpet has a power of 0.2 watts, right? And said that we are a distance of 3.2 meters away from the power source. So that is referring to the radius. That's going to be 3.2 meters. Now this is pretty nice because we don't need to change our units. Meters are the SI units, watts are the SI units, so we don't need to change any units. So everything's really already set up for us. We don't even need to change our equation or rearrange that at all. It's all pretty nicely set up for us. So what we can do is we can just plug everything in, so that intensity, you can use I or just intensity, whatever you want to use there, is going to be the power. That's 0.2 watts divided by 4 pi, and then we have a radius of 3.2 meters squared. Okay? Plug that in your calculators. All right. And that's going to be 0.2 divided by 4. And you can put this whole thing in parentheses. What I think I'm going to do is I'm just going to do divide by 4, divide by pi, and then I'm going to take that number and divide by 3.2 squared. And we get this number, a little bit of a small number. .00155, and we'll just leave it at that. And what should the units be? We have watts on top, and we have meters squared on bottom, so it's going to be watts per meters squared as our units for intensity. Watts per meter squared. And that's it. Okay? So there are no particular units for intensity. There's no new units at all involved. Do you guys have any questions? Looks like we're going to be done early today. Did you guys check out your grades for the test? They're both up on Google Classroom, and they're up on Facts. Make sure you check it in Google Classroom, because any questions you get wrong, I will actually make a note there and tell you what's wrong. The note's not detailed because I type it rather than write it out, but you'll find out any kind of things that you get wrong. What homework problems? Thank you for asking. Very good. The homework is going to be, and I'll post this here in a couple minutes. So the homework is 12A, and it's going to be 2 to 5. Numbers 2 to 5. Okay? And that's it. Homework's going to be due tomorrow, but we're not going to have class tomorrow. I'll post the answers up on Google Classroom. Okay? Any more questions? All right, cool. So we'll just end it there. If there's no further questions, have a great rest of your day, and I'm probably not going to talk to you guys until after spring break, so have a wonderful spring break. Don't know, hey, actually just wondering, what are you guys doing for spring break? I guess everybody's plans are kind of getting squashed here. I don't know if anybody's actually getting out anywhere, but we're just staying at home. I don't know if the rest of you guys are doing anything, staying at home, taking a rest, taking it easy, but that's about it. What are you guys doing for spring break? Anything fun? Or would you guys already leave me? Staying at home as well? Yeah. Yeah, I don't know. Yeah. All right. Nothing much. Yeah, me too. Nothing much. Oh, so I'm probably during spring break, I will probably get a chess tournament together. I'm going to try to set that up on either chess.com or on GameNut or something else. But so maybe we can get a chess tournament going on if anybody's interested in that. we got to do another one of Gilbert's Zoom calls. All right, fun. Yeah, Gilbert is fun. And so is everybody with those crazy backgrounds. I'll have to get myself a crazy background too. All right, so take it easy, everybody. If you are interested in the chess tournament, just email me. I've got a couple emails already of people interested, and I'm going to set that up over spring break because I think everybody's going to be staying home anyway. All right, take it easy, man. See ya.